So it's my great pleasure to introduce our next speaker, who is a very awaited here in Moscow, and he has a free talks during his visit. And Tomas Mikolov, who is working as a scientist at Facebook AI Research. Okay, let's greet Tomas.
Should I speak to the microphone? Oh, okay. Okay, thanks for welcoming me here. I will be talking today about recurrent networks and what are the good things about them, and maybe how can we make something simpler, and what can we do later, like to get something beyond the recurrent networks. That's pretty much my goal for this talk. So first, I will just summarize some recent successes of the recurrent networks and what was done in the last 20, 30 years, in very, very general way, so that we can possibly see some kind of trajectory where things are going. I will also try to explain that things can be very simple when it comes to the recent concepts of learning the memory as the state of the hidden layer, that there are very simple architectures that can match, for example, the LSTM architecture when it comes to the performance on, for example, language modeling tasks. And these simple architectures are much easier to analyze and understand what they do. And we will see that there is actually no big mystery going on. And then I will also talk about the limitations. What are the patterns that are simple for us as humans, and that are very difficult to understand for the recurrent nets, and some ideas like how we should work so that we could possibly overcome these limitations and develop models that can really understand the language, because this was my original motivation when I started working on the recurrent networks, to develop models that can understand the language same way we do, and maybe talk with us in the future, but we are far from that. So okay, so very, very basic the recapitulation of the history, people were working on the recurrent networks. Sorry? Slow. Louder, okay. I can try. So the recurrent networks were developed in the 80s by this group around Jeff Hinton. It was this parallel distributed processes group. There was a lot of famous people, and there was a lot of excitement about the recurrent nets, because in theory they can be great for modeling sequential data. This the architecture that Jeff Elman was using in his famous work. He did publish a paper called Finding Structure in Time that did get a lot of attention. It seemed like a amazing model to model language. To show some very interesting examples of what it could learn. The architecture is very simple. It's looking like this. Basically, it's some graphical representation, some simplified form, that there's some input layer here. It's denoted as some W at time t. Then there's a state of the network, which is the state of the hidden layer, called st. And then there's that depends on the current input and the previous state of the network. And then there's some output layer that usually does some classification. It can be the prediction of the next word. So it was very simple model, and at the same time there was a lot of excitement. But then did come the other works that they try to analyze these models and figure out what could be problems with them. And that was basically what happened in the 90s and later, that people actually did abandon this model because they did believe that it cannot be trained because the training is unstable, and the gradients basically either vanish or explode, and it was actually kind of a boring time for the recurrent network research, because nobody was really seriously working on that. Of course, not commonly nobody. There was for example, a group at ITSI, Jürgen Schmidhuber and his students, who were working on the LSTM networks, but these were a little bit complicated. I will get back to that later, so that they were not mainstream much at the conferences. I think that there was a breakthrough in deep learning that happened around 2010, and it was or plus minus few years. It was the same with the recurrent networks. From my perspective, there was a number of results that I was involved in at the JHU where like these recurrent networks were shown that they can actually achieve state-of-the-art performance in like language modeling and machine translation, data compression, and speech recognition. It was actually a lot of tasks, and all of them are pretty much the same, just modeling the sequences with recurrent network that work better than the engrams and other techniques that people were using before. Like the result that I was the most proud of in my thesis that I published in 2012 was the result on the speech recognizer from IBM, where the word rate got reduced by using the RNNS by like more than 10%, which was a very good result for a system that IBM was developing for like, I think, 10 years. So it was a very strong baseline. And I did publish the code, and I think that also like that helped many people to like reproduce the results. Back then I didn't actually know what's the difference to like the what people were doing like in the 90s and so on. And later it turned out that the machine learning community was not aware of this trick of clipping the gradients to prevent the instability of the training. So it seems that like very simple thing, it's completely trivial, was like crucial for getting the training to be stable and to make the networks to train, while it was previously believed that it's not really that easy. And there was actually a lot of toolkits that we can see even up to date. Like in 2010, I think the ETSIA group that published the SpyBrain toolkit, and in Montreal they were working on Tiano, and other people were working on Torch. And then there's a lot of other libraries, especially in the last few years. The companies are announcing some new library every few months, like open source code, which I think is great for getting these techniques to be very accessible. And today the recurrent networks are like applied like for many tasks, like speech recognition, but like for acoustic modeling, language modeling, similar for machine translation. There's a lot of work on that. Many NLP applications that do all kinds of things, video modeling, handwriting recognition, user intent prediction for like internet companies that try to like guess what the user will, for example, click on next, or what would he like to see. So it's a lot of cool things. Maybe everything is not that optimistic. I think that well before, like say 2010, the recurrent networks were supposed to be not possible to be trained, and there was a lot of skepticism when I was starting to work on these techniques. Like today, I think that there's maybe too much optimism. Like people just try to use the recurrent networks pretty much everywhere because there are like these toolkits that allow simple usage of these models, and sometimes I think it's more like some mysterious black boxes that people just put in pretty much everywhere, even in cases where like simple models would be completely sufficient. So I think that there's maybe a little bit too much expectations about what the recurrent networks can do. And in the second part of the talk, I will be showing that actually there's quite a bit of research that we should still do to make them learn more of the things. So in this talk, I will be mainly like trying to show that there is like a simple way how to get the longer short-term memory into recurrent networks by slightly like making the vanishing gradient problem less important or less visible. The trick is very simple, and it does it allows simpler recurrent networks to behave in a similar way as more complicated LSTM models that I think many people know here about. And this is basically a presentation of this paper that we had like last year at this iClear workshop. It's called Learning Longer Memory in Recurrent Neural Networks. So back again, like the simple architectures like this, there's input layer, hidden layer, output layer, and then the fully connected recurrent matrix. So that's what I was showing before. It's called Elman architecture because this is the architecture that Jeff Elman was using in his paper. Then there are these few equations that basically say like what we do. There is some nonlinear transformation of what we see as the features of the input layer, and what is the previous previous state of the hidden layer. Then there's the activation function, which is basically some nonlinear function. Here it's sigmoid, and there's the softmax at the output layer. So that's basically the recurrent network language model. Not much more there with the Elman architecture. And as I said, like there were these papers, like for example, Yoshia Menjo did write a paper in 1994 that recurrent networks are difficult to be trained with gradient descent. I think the title was almost like this, and many people did actually use this analysis as like excuse why these models are not possible to be trained, which was somewhat misleading because the paper actually didn't really claim that. And for the exploding gradients that I already mentioned, this is like a painful problem if people don't know about it, but there's like a simple hack if people know that gradients can explode, then simply trying to keep them in some range is usually enough, so that the gradients, as we propagate them in time through the recurrent connections, do not become huge, so that there's no big update of the weights. So like simple trick like this can already prevent the instability of the training. And of course, there are like different variants, like that we can normalize the gradient so that its direction doesn't become larger than some threshold, or we can just discard the weight updates that will be too big and so on. These are more or less like the same things. For the vanishing gradient, I would say that the solutions that I have seen usually do not really try to solve anything with SGD. Well, people actually try to solve something with SGD, like for example, at Toronto, people that publish this Hessian-free training of recurrent networks that they believe will kind of solve the problem with the vanishing gradients. But mostly the solutions were about the change of the architecture. So to prevent the vanishing gradients, which basically means that the network doesn't form longer short-term memory in state of the hidden layer. To solve this problem, like it seems the easiest to do to change the architecture, and I will show that combination of two ideas that are from the 80s can be actually enough. So I think that Mike Jordan did maybe publish it first, and Mike Mozer did work on these network architectures where the hidden layer is not fully connected, but the neurons are connected just to themselves with some weight. That's, let's say, if we think of the weight being close to 1, then that would mean that the hidden layer will be changing its state just very slowly. So it will be like motivated to kind of keep some longer time information. Of course, this is not going to be better than the unconstrained network. So people were actually not using that much this network, for example, for language modeling. But we can actually use maybe both ideas together, like both the Elman network, which is like here shown on the left side. It's like with the fully connected recurrent layer, the layer HT. And then there can be the second hidden layer that is called here ST, where neurons are connected just to themselves. So you can see it as basically diagonal recurrent matrix, where for simplicity, we can just say that, for example, the alpha value, the value of the self connection is fixed, and we can have just no activation function in the layer ST, so that if we will choose the alpha to be, for example, something like 0.95, then the state of this second layer will tend to be changing very slowly. And it seems that this is already enough to get the longer memory into the recurrent network. Interesting thing is that to obtain this model, it's actually very simple. We can just take the normal code for the simple recurrent network and put hard zeros into some places and change a little bit the learning rates for the slow part, and that's pretty much all. So it's actually very simple to implement this model just by modifying the existing recurrent network code. So as I said, like the value can be learned or it can be fixed. In the paper we did use, for simplicity, the value to be fixed at 0.95. It would work better if you would learn it, but we wanted to basically explain that very simple idea can already learn something that otherwise people used very complicated models before, like LSTM4. And then there's the matrix that connects the slowly changing layer ST with the quickly changing layer HT, but it's a little bit like detail because it helps a bit. We did decide to call the network in the end structurally constrained recurrent network because really it's a simpler recurrent network with some structural constraint on the recurrent matrix. Like one can really see it as putting some hard zeros into the matrix. Origin, we were actually calling the network slow recurrent network, but then it's like implying that the network is slow, which sounds kind of like a negative thing. Actually, it's the other way around because the model is very simple. It's actually faster to train to reach the same performance as LSTM. So actually, the advantage of the model is that it's fast, but it has the slowly changing hidden layer. So in the end, we did abandon this name and just use the structurally constrained recurrent net. So for the results, I will show like on a simple data set like the Penn Treebank, which is like MNIST for language modeling, like very simple one that people can download and just play with. It's just 1 million words. It's very simple. And then text aid, which is again like something that is publicly available, and that has the advantage that the longer term patterns are more visible there. So we will see this in the results. Also, we did publish the code for the SCRN so that people can just reproduce the results easily, and basically both the data and the code is public. I will show how, definitely you can reproduce the results that I will be showing later. And I will show how does it compare to the LSTM, which I think people know, and I think it's quite a mysterious architecture to many people because it has all these gates, and in theory it can do a lot of things, but so I was showing like the architecture with this structural constraint can just simply just forces the network to change part of the hidden layer to be moving, to be changing slowly. So that's the only constraint. And it's actually behaving very similarly. So this is the perplexity results on the language modeling on the Penn Treebank. The lower the number, the better, the more accurate the model is. So we can see that simple recurrent network is like the perplexity 29. It's much better than the Ngram baseline, which is like 141. Then there is like a simple concept from like the early 90s, how to add the longer memory also to like the Ngrams, which is called cache models, which is that I guess people probably know how language modeling works a bit. I will probably not be able to explain the whole thing, but Ngrams, just to remind people what it is, that's a statistic that's trying to break the next word, for example, given the two previous words, based on how frequently they occur together. And with the cache, one dynamically builds a small language model using the recent history of, for example, 100 words, and interpolates this with the main Ngram model. So it's like kind of like the adaptive part of the language model if you use the cache model. So that's all like helping quite a bit. It improves over the Ngram baseline by like 16 points, going to 125. And we can see that similar gains, like around 10% in the perplexity, can be obtained by choosing the LSTM architecture over the simpler recurrent network, or the structurally constrained recurrent network that's also very similar. I think that one mysterious thing about the LSTM is that it's actually hiding a lot of parameters in the model, because one hidden unit in LSTM has like 4 times more parameters than the hidden unit in the recurrent network. So I think this is something that people also should keep in mind, because often people compare LSTM to normal RNN when it comes to the same size of the hidden layer, but not same size of the parameters. So all these comparisons are a little bit tricky to do, but I will show a few more results to convince people that basically both these models learn this kind of cache-like patterns. So because on the Penn Treebank we did see like 10% improvement, which is like nice, but it's not really that much, because the Penn Treebank is very homogeneous data, and the cache models are not helping like in a huge way. We did also report results on text aid, which is like again something that data set that can be downloaded from internet very easily. We did publish the pre-processing script so that it can reproduce everything precisely as we have it. And here the cache is actually helping much more. The text aid is basically part of Wikipedia, so one can see that basically knowing the words that were in the recent history of, like, say, last 100 words is actually helping quite a bit to reduce the perplexity and get more accurate models. So we can see that here we have like drop of like 25%, but by using the cache. And again, like LSTM or the structurally constrained recurrent network, both improve the perplexity by a lot by going from the simple recurrent network. So going from like 245, we can get to like 190 with these architectures. So again, there's very strong correlation between the gain that we observe from the LSTM and the SCRN. So one can pretty much conclude that these models really learn something like cache, and it's actually very logical if one looks at the architecture of LSTM. It can be using just the forget gate to model the cache. I will be not really going to details with LSTM because I think it's quite a difficult model to fully understand, but I feel that people are using it a lot these days, so it's good to really know what it means that it relearns something on the language, like when it comes to the longer memory. This, like with the bigger models, when we did use 500 hidden units, then the LSTM was actually a bit better than the SCRN. So maybe having a little bit of nonlinearity in the memory would help, or maybe we didn't just tune the hyperparameters. Also, I should say that we didn't even learn the self-recurrent connection here. The alpha was still fixed. So it's like very basic results. I'm pretty sure one can get better than this. And still, like, the improvement is there. So we were very much convinced that this is exactly what the LSTM learns, basically the cache patterns in language. And that's much easier to understand, I think, from these experiments than from the LSTM architecture itself. So for the discussion of the results, like this model can accumulate information from the long history in the slowly changing hidden layers. So it's very, very similar to like some weighted cache model with some exponential decay. Empirically, the gains from this model over simpler recurrent network correlates very well with the gains that the LSTM is getting. And for very large training sets, it seems that this model would be preferable architecture because it is computationally actually cheaper than LSTM. As I said, for the same size of the hidden layer, it has like 3-4 times less parameters, and we can just train it on either more data or with bigger hidden layer size. So this is for this part. So just to conclude, like we can overcome at least somewhat the vanishing and exploding gradient problems that are supposed to be like the terrible problems why that convince people why they shouldn't work on the recurrent networks like in the 90s. So we have some partial solutions. I wouldn't say that any of these solutions is perfect, but definitely we can do something about it. And as I said, like recurrent networks are now getting great performance across many tasks. So I think it's very nice to use these models. There's of course the drawback that what I was talking about all the time, one can really see it as just a short-term memory that is made a little bit like longer, like more stable, but it's certainly is nothing like long-term memory. We think about the memory that we have, like if you remember what we were doing, for example, a year ago, it's definitely not some exponentially decaying weighted memory. So I think that people shouldn't really confuse these architectures with some models of memory, which is what I will be talking about in the second part of the talk. And it really seems that if we want to model the true long-term memory, then we would need some models that can grow in size, because this seems to be necessary. And I will show actually architecture of recurrent network that can grow in size in some simple way. So going beyond, like we did see like interesting result that we can like get all these like longer, shorter memories in the recurrent networks, even with simple architectures. And what are the other things, like what we cannot do? So I will focus the second part of the talk on this, because there's actually quite a few of very simple things that we can't really model easily with the recurrent nets. For example, memorization of variable length sequences of symbols. And basically, there's a lot of patterns that have very short description length, which means that they are easy to describe in human language or in computer language, but at the same time, they are not. We can't really train recurrent networks to be able to model these patterns. Like I think Wojciech was very likely talking about it in the previous talk. I actually didn't have time to see it, but I'm pretty sure it was very related. So I guess many people did already see this. So we did call these patterns algorithmic patterns. So of course, like there's plenty of these artificial problems that we can think of, but which ones are the important ones? We can think of like memorizing sequences of symbols, or solving this like counting problems like A and Bn, or maybe trying to make the network to learn in some unsupervised way some like problems like addition and multiplication of numbers, basically like general algorithms. But it doesn't seem to be clear like what's the path to like solving artificial intelligence, and how to basically get to a system that would be able to like understand the language and talk with us. So maybe it will be good to have some roadmap, and this is what we were thinking some time ago, and that will be what I will be presenting in the second part of the talk. Maybe I can just quickly stop after the first one if people have questions about the recurrent nets and the longer memory, so that we don't have to get back to it later. Then just ask me right now. Okay, okay.
We need to broadcast them, so if anybody wants to ask the question, go here.
You see, it seems there is if anybody tried to use just small noise to fight with this vanishing and exploding gradients, just when it goes to zero, add noise, and also when it goes to limit, subtract noise, something like that. If anybody tried that.
Well, I didn't see this. Definitely, people try to use edit noise to fight, for example, with the overfitting and to help the regularization. So, for example, you can make the network quite a bit bigger, and then you will be adding noise. And this is basically what the dropouts are doing. So this is like a way how to help the network to regularize. I wouldn't say that it helps the network to learn a longer memory, but in your case, you would probably be adding noise to the gradients, right? So that they will be basically non-zero for a longer time. I didn't see a paper like this, so I don't know.
Any other question? Yes, please.
Thank you for the comparison that you have presented. You compared the model here in terms of perplexity, so it is based on the likelihood that the model tries to optimize, right? So my question is, in your experience, how does perplexity correlates with some end applications and quality, extrinsic quality?
Yeah, that's also an interesting question. So also the answer would be maybe a bit long. So because there are like several things that are mixed together. I mean, in the practical evaluation, like people did know for a long time that perplexity, for example, it's hard to say how it correlates, for example, with water rate that you obtain in speech equalizer or with the blue score that you obtain in the machine translation. So one popular saying is that the cache models are actually not helping much for these applications, and maybe like focusing just on the short context is enough. This is slightly misleading in the sense that, yes, it's true that these cache models are helping much less for like the water rate, but then you can see like papers where people, for example, claim that LSTM is like way better than the simple RNN and so on. That comes with the problems that usually people compare models with the same size of the hidden layer, so the LSTM actually hides a lot of parameters inside of every single neuron. So they are actually comparing models with two different sizes. One is much bigger, and of course, then it can be actually winning just because of the size, not because that it models the cache patterns. And one more like story, just to make it more confusing, is that also like people were aware of the problem already. Like I did hear the story from Dietrich Klackow from the speech recognition community that the way how the perplexity is evaluated is also like a bit like not very good in the sense that you evaluate it on actually like a real clean text, while if you are using the language model in speech recognition machine translation, your history is noisy. It's basically the hypothesis. And then if people would actually be measuring the perplexity gains from the cache models in the cases where the history is uncertain, then actually the gains became much smaller. So this importance for the longer short-term memory in like speech recognition and machine translation on the language side seems to be smaller than the perplexity gains would suggest otherwise. Yeah, no problem.
More questions?
It's okay.
Hello, I'd like to ask a question about preventing gradient explosion. I'm interested in your opinion. What is better to use? Is it clipping or normalization?
Well, in my opinion, both are doing pretty much the same thing. Like with the exploding gradients, you have this effect that basically, as you are propagating the gradients back in time, they can be like, say, multiplying at every time step they are like normed by say 3, 4. And then if you go like 10 steps, it's already like in millions. And then you will make like a huge jump in the weights and you would completely destroy the network. It's terrible. So even if you would forget about the clipping or or normalization, you can just say that whenever I encounter the situation, because the gradient explosions are quite rare for like well-chosen hyperparameters, I don't think it's actually possible to get rid of them completely, but there are always some chance that the gradient will be exploding, but because it's just for a very small subset of the training data, maybe you can just like completely discard that update of the weights whenever you see that something was going wrong, which goes maybe to some slight extension to this gradient clipping that I didn't publish, but I think it would be also very useful. Like the gradient clipping itself doesn't guarantee yet that you will actually not really get into some bad part of the basically the training will not start diverging. So it's even, I would say, better, at least it was in my experience, if you would look at more like the change after some time of updates, like because if you look at the gradient clipping, it basically does not prevent the network to do like say 5 or 10 updates of the weights in some direction. That's not very good, and then it can actually jump into some part of the space where it will start diverging. So maybe they're like discarding the problematic patterns whenever we see the gradient exploding, maybe just setting everything to 0 or probably skipping this update, or maybe like looking at like a few recent updates and just keeping some track of what was the best weight settings that was working the best, and maybe you're like running some small comparison in the like with a model that is not changing its parameters and the one that is changing the parameters. And when the one that is changing its parameters starts to behaving crazy, then you would get to the backup copy. Like, I think there's a lot of strategies that you can come up with that will be pretty much like more advanced than the gradient clipping and would be doing something similar and would be actually like more resistant to yeah, I think that there are like algorithms that are called that were used in the search community that were like trying to like just move when you can really get to better position. It doesn't have to be really better in this case, because even if you measure the performance of the last 100 examples, it can be actually a bit worse. Doesn't matter. Just you would look at when the network starts behaving crazy, then you would just like discard this one and go to the latest one that was still working well. So you would save some backup copies. That can be even easier than the gradient clipping. Then you don't have to tune any clipping threshold. Only say that when the performance of the one that is changing, the one that is learning, is on the last 100, for example, training examples. Exactly, that's what I was getting to. Then you would say that if it's like, say, 5% worse or something, then you will be just getting the backup copy or something.
Okay, the last questions, and we will go further.
Can you say why don't you compare your algorithm with some other synchronous models like GRU, because they are seems like cheaper to compute and
I think
LSTM.
Yeah, definitely. I think that will be interesting to compare. We did just publish a paper, I think, in the same month as the GRU. So we did like no after we did publish the paper that this like alternative structure that the Montreal guys did publish, because they are also not happy with the LSTM complexity. So the motivation was very similar. I would say our model is even simpler because we don't have any gates there, and it seems to be sufficient for language modeling. If you would go to like different tasks where you have to learn something like some nonlinear transformation of the features to store in the longer memory, then you would probably need either the structurally constrained network with more than one hidden layer, like a deeper model, or you would maybe need to use some gating mechanism too, and then it will be getting quite similar to the GRU. So I think that these areas are quite related, and we would definitely compare it if we would continue working on this and publishing some further paper, which may happen. Yeah. Thanks. So as I said, like with the recurrent networks, it's like great, for example, to look at the text that we can generate from these models. I'm pretty sure that many people did see a lot of examples. It can be looking quite convincing that the model learns something about the language, and then we can train the network even on bigger data set and tune the size of the hidden layer to be even bigger, and the perplexity is getting down always, and it seems that it will at some point understand the language and be able, for example, to finish conversation for us. Well, yes, if we would have infinite amount of data, then sure, but I think that it's not going to happen that we would be able really like to have a dialogue system based just purely on the recurrent network, because we are actually missing quite a few components there, like the system basically is not really motivated to do anything else than prediction. So if you want to develop like a perfect language model, something that that would be like a system that can like communicate with us and maybe like predict exactly like the next sentence that would make sense in the current context, we would really have to change the objective function and maybe even how the model is learned. It's very, very fuzzy and not simple to see what would have to be done. So we did define this this kind of like roadmap how we can go towards the machine intelligence, and we did it the other way around. So instead of saying at first like trying to build some more and more complicated models to solve like say a simple problem like language modeling for us, we did go the other way around. So first we we say what we would like to achieve, and then we are trying to simplify this so that or simplify the plan so that we would be able to see some small goals that may be achievable. So the ultimate goal for us is like a system or a machine that will be like truly like intelligent, like from the science fiction movies, or like something much bigger than speech recognizer. So a system, for example, that can understand the language so well that it can, for example, communicate with students to help them understand what they are trying to learn, understand the homeworks, and so on. Maybe even help researchers to find relevant information. So instead of like just having some kind of dumb search engine that is just trying to like guess what we want to find based on the keywords and how keywords appear in documents and what people were clicking on before, there is something that will be able to understand what we are searching for and will be like helping us to find the information much faster, which I think would be great. For example, if you would ask now Google like show me a paper that explains what LSTMs learn from data in language, then I think it will be not giving you very relevant responses. So maybe this future system that we aim for would be able to do that. And even further, like communication-based AI can be seen as a replacement for programming. It can be seen as a system that we would be basically talking to the computer and ask it to do things like instead of like typing all this code that we have to do today. For example, if we want to have some web page and we want to see some buttons here and there, we have to like write all the code. We can't really say to the computer like put this button here and don't do this again. And so like it just doesn't work that way. So it seems that the AI can clearly change the way how we communicate with the computers, like replace the artificial computer languages with the natural languages would be like saving so much time to people. And the same with like scientists, like they're like if the computer would be able to like think and communicate with us, then it can do like independent research for us. It would be like really like amazing. So these are like the biggest goals that we could think of. And well, how to get there? I think that we have to like define some minimum set of components that we would need, because if we define too many, then the plan would get confusing and it would be clear like what has to be done. It will be difficult to see it even with the small set of components. If you would have too many of them, it would be completely impossible. And then we can think of some approach how such machine can be constructed that will be able to communicate with us. And this is what the second part of the talk will be. So we did in the end decide that the things that we can't really remove from this useful communication-based AI is definitely the ability to communicate. Like if you remove ability to communicate from AI, then you can have, for example, a machine that can play like, for example, StarCraft very well or some computer game, but except observing what it's doing, or maybe chess or Go as is popular these days, you can observe what it's doing, but you don't really have like a way how to ask the machine to actually do something for you, because there's no communication channel. So this seems to be like necessary to have the ability to communicate in the system. Again, like it's also something that we don't really have in the language models. Like they are not really talking with us. They are just like trying to model the sequences, and that's their objective function. So related to the ability to communicate, we have to be able also to motivate the system to do something, because if we would be able to communicate with the AI, but its objective would be something that we cannot influence, then the AI just doesn't have to care about us and just do nothing useful for us. Of course, such system would be also like kind of sad to develop. So the motivation component seems to be like completely like crucial as well. Like we can't really get away without it. At least it seems so. And then Then the learning skills, like I think that's very obvious, but maybe it's still good to say that the intelligence is really about being able to like learn like any kind of skill or solution to any task. Like that doesn't mean that the system can really like solve everything, but that it is able to learn like anything new. Like it seems to be like very necessary that the system is not some rule-based entity that is scripted to perform like thousands of tasks that the programmers did anticipate, but it really has to be a system that can learn like a new task, and through the communication and through the motivation, which implies also like some form of long-term memory, because if we think of the AI as something that knows some set of skills and has the ability to learn more and new skills, then it really seems that it will have to extend itself and learn new things. So, so we did think of some framework where we can build such intelligent machine, because we'll probably need it to be able to run experiments and develop techniques, and this is what we did in the end after a lot of discussions. What we did end up with. So it seemed that simulated environment would be much better than building robots in the real world, because that just comes with a lot of complications that we want to avoid, because there's a lot of failing cases that we will see even in very, very simple cases in simulated environments. Then it has to have the communication channels so that the machine can communicate, some rewards that are related to the motivation component, and the framework should have some incremental structure or maybe hierarchical structure, so that the learning can become like more similar to like how the natural intelligence develops in the real world. Like we base our skills and our understanding of the surrounding world based on what we did learn before. So it seems to be very, very crucial. And again, this is something that the standard machine learning techniques are not able to deal with. So there is no such data set that would really allow to teach the machine the communication skills in the way as I was just describing it now. So we are like describing such environment in our paper, and we plan to construct it in a practice. There's a lot of like things that can go wrong. Like if we would add the complexity to the system too slowly, then we can end up with something like what happened to the NLP community, where people did try to downscale the final goals of language understanding to something like more well-defined goals, like tasks like part-of-speech tagging or parsing and so on. And they stayed later, like for 20 years, working on like improving the parser from 95% accuracy to 96. It wasn't very clear to many people like what is the point of such work, because the parsers themselves are not like that much useful, and what is the extra 1% of accuracy going to get for us? And definitely didn't lead to language understanding. So we definitely need to be ambitious about the speed at which the system develops, but at the same time we would just go other way around and say define a task like let's show the machine like these tasks for like 8th graders, and just expect them to like the machines to solve these problems with some machine learning techniques that we have right now by showing it a lot of examples. But maybe it's like adding the complexity too quickly. Like we are nowhere near solving even like problems for like the 1st grader, not to mention 8th grader. So like not asking too much, but being ambitious, I think is very important, so that we keep developing new things, and at the same time have chance to actually develop new things, so that the complexity is not too high. So the description of the environment that we are thinking of is having few components. There is some learner, which is how we call the machine intelligence. It's like the entity that that does all the learning. Then there's a teacher, who is the entity that gives goals to the learner. And in the beginning, it's scripted so that we can produce a lot of experiments very quickly. But later, it's supposed to be replaced by a human who would be actually giving goals to the machine. And then there are the rewards that basically the teacher can give to the learner. And then there are like the obvious things like how to scale this up. Like we definitely believe that if the simulated environment is going to lead to something scalable, then we need to be quite strict about how much supervision we give to the system. Like we shouldn't give it too too many training examples. We shouldn't really give it strong supervision by telling it what it should have been doing in this situation. We would be just like lying to ourselves, and of course we can then solve like the simple artificial tasks, but then it wouldn't scale up. So this is what we discuss in the paper quite a lot. And then we can, of course, later add the communication with real humans, but we are, again, like quite far from developing techniques that can learn quickly from few examples new skills. And of course, system that can communicate can also be connected through ability to form queries with internet, and then it can actually have plenty of real-world signals if it would want to. As for like the agents that we have in the system, there's the environment that there's like very simple, and it's of course again scripted, and that produces some basic signals for the learner. I will show just in a few slides graphical representation where it will be more obvious. The learner, as I said, is the intelligent machine that has as a goal to maximize average incoming reward. It sounds very similar to what is done in the reinforcement learning, but we really want to do slightly different things than what people do right now. We definitely believe that the amount of reward should be really low, and similar, for example, even like what people did write about reinforcement learning like a long time ago. I remember like during a nice discussion about this, like we definitely cannot expect to get like rewards at like every second of the life, and we cannot expect the learning to be based around such concepts. So the reward has to be really like sparse and really useful, mainly in the early parts of the life of the learner. And then there's the teacher, as I said, which is the agent that represents in the first place, in the beginning, the human. It gives tasks to the learner and then measures how well does it do, and rewards the good behavior and so on. So as I said, like crucial part of the environment is the communication. There are these communication channels. The teacher and the environment can write to learners input channels, so they can basically communicate this way, and the learner can produce its outputs in the outputs channel. And then there is this special part with the rewards. So the graphical representation looks something like this. It's like a computer game where we have the input and output channels. The input channel is shown on the left side, the output on the right side. So this is an example where basically the teacher specifies a command or a task that is like very simple, like move and look, and this is like something that the bot can read sequentially. It's basically running online, and then the output that the bot that it already learned to perform this task would be like that. He addresses the environment and says I move. Then there's like a next step where he already did move. Then the environment confirms that he did move by saying he moved, and then the learner continues because it has the memory of the command. It was able to parse it and produces another atomic instruction, I look, and then the environment says there is an apple, which is not that crucial. The teacher already rewards the learner for performing the commands that he asked for by giving it reward. So simple environment like this, it might look trivial. It definitely will be super trivial to hand code the solution, as everybody can imagine. The tricky part is that we want to develop a machine that, by observing like commands, which are basically some sequences of symbols, and then some rewards, would be able to really like maximize the learning rate, in a sense that it would be able to learn to perform the tasks from as small number of examples as possible. So as you can see, there's very little supervision here, and it should be getting even lower later when the commands that the teacher is asking can be composition of other skills. So we give some examples in the paper. I'm not gonna go into much details here, but it may look trivial, but it's actually very challenging. I will show it just in the last part of the talk, that very, very simple patterns that can occur in the simulated world are already like beyond what recurrent networks can generalize to. So the scaling up, as I said, like we have to be quite strict in the beginning by requiring the machine to do a lot from small number of data, small number of examples. So we really want the machine to learn quickly. And as I said, the objective is not just to get like, say, 90% accuracy on some task, but the objective is to get to good accuracy in as small number of trials as it can, because otherwise we can be really fooling ourselves. Like I think that sometimes people like misinterpret the result that one can achieve, for example, with reinforcement learning by showing too many examples to the machine. Like you can think of like playing these Atari games that are now popular now. By playing them on like 10 times more computers, of course, you will get a somewhat better score. But in the end, it's more like because you did explore like wider search space, not because you did develop algorithms that can learn faster. So I think that we should really like change the focus. It shouldn't be like about the end performance, but about how long it does it to get for the machine, how many examples does it have to see before it gets to this performance. It's very related to like how would you expect the artificial intelligence to really work. If you tell a human to do some task and the human basically fails for like 10 years before it learns the task, then it's not a very intelligent human, and we want actually to develop a machine that doesn't need to hear the command like in like thousands of variations, but something that can generalize fast. And that's why the objective function should be really about generalizing fast. So that's also why we don't think even about the distinction between training data and test data. We just think that everything should be seen as test data and the machine should be training continuously all the time. As I said, like adding humans would be great in the end. I think many people have this question normally, like how to scale from the artificial data to real world data, and how to get the humans and how to deal with the variability in the language. I think these questions are a little bit overrated because we are nowhere near solving even much simpler things that are definitely solvable because the machine learning techniques that we have now, like for example, the recurrent networks, struggle even with simple algorithmic patterns, which I will be showing just in a while. And as I said, adding the real world can be also like easy. We can simply allow the machine to access internet through the input-output channels. So this is definitely doable, and the machine can, in theory, learn a lot by reading the Wikipedia and just doing a lot of things unsupervisedly. But this is like a long-term vision that we are nowhere near that. So why was I saying that we need new techniques? Well, because there are some very simple patterns that the recurrent networks do not really learn. They more or less like memorize them. So they are very bad at generalizing from like small number of or any number of training examples to novel test data. So for the scalability, I think that there are like several things that we discuss in the paper that we believe that will be necessary. Like as I was saying, like there has to be some chance for the models to develop long-term memory and store not just the data in the long-term memory, but also the skills. It's kind of tricky, and we are not completely sure how to do it yet. Then the model should be like computationally complete. Like it's easy to see that human language is Turing complete because we can say infinite length description of any algorithm. We can also write computer algorithms, and we can define the Turing completeness in natural language. So we don't have problems with that. It's funny that actually most of the machine learning techniques or models are computationally limited, so they can express just some subset of regularities in the data. Then we also like believe that because humans really learn like by going to the first grade, second grade, third grade, and so on, very incrementally, like they base the their new skills on the previous skills, and this this hierarchical learning, also like it used to be called incremental learning. I think Ray Solomon was working on it like from the 50s. It's like it seems to be like very important piece that we are still missing in the machine learning. Like we don't really know how to solve it well, so that the machine will be actually learning faster and faster when it's encountering patterns that are or tasks that are just small variations of the previous tasks. It's actually the other way around with the recurrent networks. They or with gradient-based techniques in general, they would rather learn slowly whenever we change the task to different distribution. And then, as I was saying, like definitely, like keeping the number of examples small should be the objective, and the rewards should be as sparse as it gets. So for like our ideas how this can be solved, or at least the direction, we did publish this paper on like stack augmented recurrent networks to learn the algorithmic patterns. The idea is very old. We are not the first ones to realize the limitations, the computational limitations of recurrent networks. People did work on this like in the 80s, 90s. I think that there's even older work. I think that a large part of the Perceptron's book is about limitations of neural nets. I'm not sure who is the first one. Well, many people cite Das and the others from I think 1992 to work on like this stack augmented networks. I think Mike Mozer was working on it too around similar time. It's actually difficult to say who was the first one, but definitely there was a small group of people who were trying to overcome these limitations of neural nets and their fixed capacity by having these long-term memories, where the stack is the most simple one, like in computer science. So what, of course, one can ask what is the difference in our work to this work in the 80s, 90s? Well, we did read the papers and we realized that actually our model that we developed was quite a bit simpler than what people were considering before, and that we also didn't need so much of the strong supervision as people were considering before, where they were sometimes really telling the network what it should have been doing with the stacks. We don't say anything like that. It's using the stacks basically just some topology on the state of the hidden layer. So here is like the simple visualization of the model. So again, it's some kind of recurrent network that has this action component. So it's shown with a single stack, but it can have actually multiple stacks. Usually we use multiple stacks, and the hidden layer basically uses the current input and the previous state of the stacks to decide on the action, and the action is like a softmax between three operations. Either the network can push some value, and the value that to be pushed is also learned through SGD. Everything is learned by SGD. Then the network can also pop the topmost value, or it can decide to do no operation. Of course, one can very easily define like very similar like memories, like lists or tapes and so on in very similar way. So basically, it's like the action component that says what action will be done, because it's there's a softmax. It's continuous mix of all these three operations, and then the hidden layer says what will be the topmost value written there if it decides to push. Maybe I can just say how the model is trained. Actually, this is more described in the paper, but it's very similar to the structurally constrained recurrent network, where we did say that you can have the diagonal matrix that basically keeps the states of neurons to be the same, which can be already seen as the no operation, and the push and pop are basically off by one diagonal matrices, so that if one wants to push the value on top of the stack, then basically all the values are supposed to be pushed by one position down. So it's really like off by one matrix. And if you want to do pop operation, it's the analogy. So it's the other way around. So you are pushing everything up. So again, it can be seen as a matrix where every neuron is connected not to itself, but to neuron like up in the hierarchy or down in the hierarchy. And then the action basically is like the softmax that's working as kind of like a gate to this operation. So everything is actually pretty simple in the end, and it can be trained with SGD and backpropagation. So we didn't need the reinforcement learning or any of these complicated things that are hard to make work on these problems. So here are just some examples of what we considered in the very beginning, like it's these simple grammars that even LSTMs would be able to learn because they have the ability to count. And it's like this A and BN and so on. Here is basically shown what the network has to do. Like, let's consider just the first one. You have like a sequence of A's and B's where the number of A's is stochastic, so it's chosen at random. For example, we choose to have 2 A's in the beginning, then there's 2 B's, and the symbols that are shown in bold is what the network can predict deterministically. So once it sees the first B and did it see before 2 A's, it already knows that there will be 2 B's, and after that there will be 1 A at least. So this is shown in bold. And then we measure the accuracy of the network to predict these predictable symbols. It's looking like this. Basically, we can more or less predict everything with some tuning of hyperparameters. It would work well. So this is already like better than the work in the 80s, 90s, where people, I think, were a little bit struggling already with the counting patterns. But it's very, very like toyish, of course. Even LSTM can do it because it has the linear component. And so the stack RNN would be the strictly constrained recurrent network could possibly solve it too. So that's like basically just one small step. The other step is when you try to work with the sequences, which I think is sort of getting more interesting. We can easily break the LSTM because one can maybe count with the linear units, but you can't really have this inflating memory. So if you want to store some sequence of values that has variable length, then understanding this concept without being able to express the algorithm is not really doable. In the same way as finite state machine would fail here, and we could actually succeed to solve like memorization of a string in reversed order, and then binary addition also in reversed order. It's quite interesting. In the next slide, I'm actually showing what the network was able to learn, where we did give it 10 stacks, so it doesn't have just a single stack, it has 10 stacks, and it's shown a lot of examples where it just sees examples of some calculations where you have like a one number, then you have a second number, then you have a result of the addition, and this is how the sequence is composed. You just show it plenty of these examples of sequential data. You don't give it any supervision. You don't say where the result starts or anything like that. It has to figure it out unsupervisedly. That when there is the equation symbol, then it has to be it has to start predicting the result. So it's quite interesting that it was able to learn it, because as I said, it's still like the most basic things like stochastic the gradient descent and backpropagation to time. And just to explain what it does, basically learns to store in some of the stacks the first number first, basically the information from the first number. So it actually doesn't have to copy exactly the digits. In one case, it actually stores the digits in the opposite way because it's just enough. So it stores the information about the first number, then the information about the second number in different part of the stacks, and then it's using this information by calling the pop operation, which is the red color. The green color means push, the red color means pop. So first it's pushing these two numbers, and then it's popping them out and predicting correctly the result. That also requires it to develop this mechanism of carryover, and it just does it. So it was actually kind of surprising. I didn't expect that we will be able to do this. Armand Julien spent like a month working on it, so in the end it works, and the results are reproducible. We did publish the code, so it's not just like some fancy thing that nobody can reproduce. The model also like is Turing complete computational model, so in theory it can model any computation as long as it's using at least two stacks. Of course, that doesn't say about the efficiency of the computation. If you, for example, wanted to store the sequences and reproducing them in the original order, then it would be quite challenging to do that because the stacks have very, very like hard structure. Well, still on the good side, it's like a model that has at least some simple form of long-term memory. So you can like, once you learn these algorithms, then you can possibly like predict much different test examples than what you did see during the training. Like, for example, much longer sequences, especially if you would use some quantization to deal with some simpler artifacts. And it's like really going beyond what the normal recurrent networks can learn, and LSTMs as well. So we think that it's like interesting. Of course, like the bad things are that we didn't solve everything by far. Like the long-term memory is very simple. It still learns like the logic of, for example, the binary addition, the weight matrices of recurrent networks. So if you would train the network to do, for example, binary addition and then do binary subtraction, and then maybe try to do binary multiplication, each time that you change the task, it would have to retrain itself, and meanwhile it would forget everything about the old tasks. So it's actually not able to use the long-term memory to store the skills which would be great to solve in the future. We don't know exactly how to do it, but it seems to be necessary for future. We can't really have hierarchical learning if we can't form a hierarchy because the models are fixed sized. So the other bad news is, as I was saying, that stacks do not seem to be very general choice for the topology of the memory. We can model some basic algorithms quite well with them, but still the same as computers are not the same as Turing machines. They are maybe Turing complete when it comes to the ability to represent in fixed size any algorithm, but they are like random access machines. So it's different. If we would be using computers as Turing machines, they would be super inefficient when it comes to access of information. They would have to cycle here and there all the time. It would have very bad time complexity. So that's pretty much for the downside. So for the conclusion, it seems that if we want to develop artificial intelligence or system that can understand the language, then we should really set very ambitious goal in the first place. That at the same time seems doable, then try to see some steps how we can get to accomplishing this goal without actually intentionally cheating. Cheating is very hard because people often would like to add more supervision and more training examples and so on to help the model, and then it solves next task and then fails completely to generalize later. And then it seems that we will need to develop new set of tasks because, as I was saying, we don't have any framework for learning language right now. Definitely Penn Treebank is not perfect for learning language. This is not how people learn language, by just reading a huge number of newspapers or Wikipedia without anybody telling them anything about it, without any ability to communicate and talk about what they are reading about. It's very different. The current machine learning techniques are much closer to statistical techniques than to AI techniques that we would like to have. And we also need to develop new techniques, and for that, it's very related. We have to develop both the tasks and the techniques to make some advancements. And then, of course, it would be great if more people would be thinking of these problems and trying to come with the solutions, because the more people will work on in this direction, the faster progress we will make. So that's also the reason why I was presenting it here. So that's pretty much everything. So thanks for the attention.
Thank you, Tomas, for the great talk. And I will use my position as a organizer to ask your first question. If you take into account all your requirements for the tasks which we should set to the system to grow it up to the, say, true artificial intelligence, can you estimate if things like Minecraft, where you have a lot of children playing the game, can they provide such type of environment? For example, you can easily imagine fitness function, like that child can create something like smart cube or something like this and interact with it, and so, and destroy some cubes, or some cubes will be discarded, and then you can learn easily. So first you upload the simple model, and it is very important that here you have right to have an errors, because you play with a child, and they can just tweak, and it can be funny for them, all these errors. So you can attract their attention for a lot of time, and also you can have something like an evolution of your architectures, because if you know that child prefers some agents, some variants of your architecture, you can replicate it, you can tune it, and the architecture can learn from the interaction. And also you have a distribution of ages in the game, so you have different complexity of communication and stuff like that. So what do you think about this?
Yeah, thanks for the question. Actually, some people who are involved in this project were also thinking about the Minecraft as possible environment in the future. It's definitely one of the ideas that were around, and it can happen to be similar to this later. I think that in the first place we would have to develop the techniques like the agents and these machine learning techniques that will be able to do what I was describing, basically be able to learn different skills in their long-term memory, which is something that right now it's not really the case. Like if you look at what say recurrent networks do, you always like rewrite all the weights of the network with whatever you see right now. You are optimizing the gradients with respect to all the parameters. It's not that the network can choose that it will be just updating some number of parameters and keep the rest like sleeping and kind of develop these kind of skills that will be like orthogonal to each other in the long-term memory. We don't have techniques like that. So of course we can go directly to Minecraft, but that's the danger that I was saying in the beginning, that maybe people would want to go a little bit too fast, and before we actually have any techniques, we would be going to Minecraft. And I'm pretty sure that even with the current techniques, we'll be actually able to see some interesting behavior, and it would be very difficult to say once it would start failing, what is the reason. That's why maybe trying to isolate the problems and getting to the core of like the inabilities would be good, so that we would, for example, focus on like techniques that can form this long-term memory in like artificial environments, like very simple ones. In the same case, for example, you can look at the perceptrons book where Minsky defined this XOR problem and the parity problem. He was able to show like if you don't have any hidden layers, then you can't really solve this simple thing at all. And if you have like one hidden layer, it will have to be like exponentially large if you want to solve the parity problem. So you will probably need more of them. And then you look what happened like 30 years later, like people started working on deep learning, and like it's not that surprising because they're like these limitations of the shallow networks were already like known before. So I would say that if we can really like isolate the core fundamental problems, the computational limitations of the models, and try to solve them, and then like scale it to Minecraft and the other games, then that would be better than doing the other way around.
Oh, okay, thank you for the answer. So, Evgeny.
Hi, my name is Eugene, and the question is the idea of say artificial kindergarten is very interesting because it can generate potentially infinite number of samples to learn, and we can greatly accelerate the progress. But it seems like it's very abstract environment, but requirements are to communicate with a human who is in a very specific environment built by nature. And latest, I would say, scientific discoveries in neuroscience say that maybe language is grounded in our nature, in our embodied language. And so having abstract environment does not seems like to bring all that layers that we have in our language that seems like bound to our environment. Don't you think that we try to skip some steps with it? Maybe we have to not simulate the evolution, but to use some layers that are not require complex tasks from the beginning, like in your examples.
Yeah. Well, I think that that's actually some worry to have, because you can think that humans actually, before they learn language, they already understand a lot about the environment that we live in, like about the real world, and the machine that we would want to learn and learn the language in the simulated environment actually doesn't have any prior of like that there's some like physics or like two-dimensional structure or three-dimensional structure of the world, and that there's something like time, and so like it has to develop this understanding from like a very simplified signal. That's why I was a bit skeptical about working like these very algorithmic tasks, like for example, like binary addition. What does it actually says? Like if we go from binary addition to like binary multiplication, some people actually did at Google. Like, is it actually that big progress in the right way? It seems to be like quite different to like our learning. That's why we wanted to see these like very simple tasks, but in simulated world, it will be closer like to like a simplified version of our world and simplified version of the task that, for example, children and living organisms have to accomplish, which means like going somewhere, maybe picking something, eating something, returning, remembering the path that you did go, and basically forming these skills.
But
So,
even in this case, you have learning from something like a blank slate in your environment. But in real animals, they have a lot of innate knowledge about their world.
yes, and we may actually have a lot of innate knowledge, like about like our like basically instincts that tell us what to do in the world, that can actually help us a lot in the beginning of the learning. That's why I think that actually the whole beginning of the learning will be like very difficult and crucial. I think that we can overcome this this limitation of not having enough prior knowledge in the system by defining a lot of tasks that will be like maybe simple to us, but will be actually giving basically the prior to the machine. Like similar, like if, imagine that you would wake up at a completely different planet and you would be supposed to learn something there. It would be much more useful to you actually to go through like very, very basic, simple tasks in the beginning, so that you can build kind of like a prior over possible functions that you see around yourself.
Yes.
What are these basic tasks you give?
Which task?
Which task would be what simple task?
What is your list of the basic
basically
tasks?
what I was showing, like something like just being able to parse simple commands, like being able to repeat, for example, what the teacher says. Like it can define like a simple like a task that would be just to repeat the last command and observe what basically the environment is producing. Of course, what I was showing looks simple, but we were considering even much simpler things where you would be just repeating basically substrings and learning that there's like something like you are paying attention to something in your input stream and you are producing something in your output stream, and being able to relate these without actually encoding this into the machine in a hard way, but having a machine that can discover this through some tasks. So, so I think actually that learning of the most basic things is much more challenging than later scaling it up to like communication with humans and so on. Like once we have a machine that can like form this kind of structured hierarchical memory and base the next solution to the next task on like previous sub-solutions, basically see the new solutions, like combination of previous knowledge. Once it has this, then I think much of the artificial intelligence is already solved. And then the other things like learning of what is the capital city of France or whatever, like all these knowledge-based things, I think that that will be much more easy to get into the machine than the like general learning skills. So I would like to focus really like on that. And I definitely agree with you that it's going to be challenging and maybe counterintuitive in some places, because like we humans are already born with a lot of hacks that are helping us to do this, which can also limit us in some way. If you look at the animals, like many animals are actually born already with the ability to like run and eat and so on very quickly after they are born. But then later in their life, it seems to be limiting them, and they are not able to learn that much more. Like maybe also like humans are that good like in general intelligence because they are born maybe with less prior knowledge than other animals, and it takes them like many years to do basic things like walk and run. It takes like years. So maybe actually having less prior knowledge and allowing the system to kind of learn how to learn, like learn these meta learning skills, is like a big part of general intelligence.
I have another question. On one of the slides, you have when you have a definition of your interfaces between agent and environment, you have a reward as an external signal which is given for the agent. Do you think that it is appropriate architecture? Because in the real life it is other way around. So the agent really has no reward signals from the environment. It just recognizes some environmental states as rewards. So its reward is calculated inside the agent, but not given to it. So is it?
Yeah, and I think in the end it can be like seen as this. Yeah, I understand what you mean. It's maybe a little bit about the terminology, how I did present it. Of course, sure, like the agent kind of like gets to some situations. It's not that somebody's giving you the reward, but you really get the reward. Like your own brain basically has these hard coding mechanisms that tell you like which situations based on the receptors are the good ones or bad ones. So maybe we can just change the terminology there a bit. So, yeah.
Okay.
Hello again. Two really small questions. First, I understand correctly that the data structures are in this kind of models are able to access in some undefined, priorly undefined quantity of memory, or is it like stack is encoded in a weight configuration and the methods by which the system accesses them?
Well, basically the growing part of the model is supposed to like allow it to be like Turing complete. Like if you look at like being able to learn irregularities in general, like that's like the very old result that you need the Turing completeness. For that you need some topological memory, which is always defined as some infinite simple structure that has some shape, and then some maybe finite controller, always finite controller that operates on top of this. So this is basically what we try to achieve. Like, of course, if you would ask concretely about the stacks, as I was saying, like it doesn't seem to be like that if you just have Turing completeness that you already did win everything. Not at all. Like there's the time complexity issue that some Turing complete systems are like having time complexity that doesn't seem practical at all. And that's why modern computers are actually not Turing complete. And in the paper, we actually are like the most convinced about like some parallel computational architectures like solar automata and solar systems and these things that basically part from the computational parallel, and that's more similar like to neurons in the brain too.
Is there possible a situation when system tries to write into the infinite like memory tape like all zeros or all ones, and it's runs out of the memory in the system that which simulates it?
This thing, yeah. Well, basically every real computer is actually not Turing complete in the strict sense because it has limited capacity. So sure, just we can consider it as Turing complete until it runs out of the capacity. So for like some practical executions of algorithms, it can actually be Turing complete if you don't run out of the memory. And that's how we think also like about our model, that we think of like, you can think of some growing data structure, and basically the whole point is to be able to basically always add one more thing. Of course, if the physical machine actually will not have that memory and then it will fail, it's already like another issue. Like we again like are nowhere near that point yet. So yeah, we didn't really consider it very seriously yet, because then you can think of like how much of the memory even like you would need to represent these kind of computations. Like whatever we did learn so far, you can see there's basically like a few instructions or few states, and maybe if we can learn like something like equivalent to 10 instructions with the SGD and so on, like the binary addition, I don't know how many it is. So it's not really that much memory that we did need so far. So I understand the question, but I think we are still far from getting to that point.
Yeah, got it. And another one is there maybe an idea how to encode in this kind of architecture the property of maybe trying to discern an abstract cause, or maybe abstract some intermediate step? Like in this case, you have like carry the one procedure, and it's learned by the system. And if we were in some abstract new universe or like on the planet, and we see that like leaves are moving, and we don't presume that trees are like alive and animated by themselves, but there's a third like abstract invisible reason of wind that is moving those leaves. And is there a way to maybe make assumptions in this kind of system about intermediate steps or intermediate actions that exist out in the world, and try to find them?
Yeah, this is like quite complicated question in a sense that there can be like multiple things that could be discussed. Like you can think of like if I would just answer it very broadly, like you have the rivers that I was talking about that are kind of like the system is trying to optimize the rivers, especially in the beginning, but I was getting to the point that there should be less and less of the rivers, and the system should be getting more and more unsupervised, in the sense that it should be like still thinking of the rivers the same as children are, like that you will not touch fire and so on. But like adult humans often like optimize kind of like their own rivers. We develop kind of like our own beliefs about the world, and maybe why the leaves move, and maybe we create some theories of why this happens. Maybe we can create the same way like the religion and so on, by composing a lot of like beliefs about something that we maybe don't really know how to explain because we don't know all the details, but we still have the theories. And if you have a system that can basically set goals for itself and develop its own kind of thinking, in the sense that it can like put or create basically thoughts and store them in the memory, then this is how I think about the AI, basically a system that it's a composition of thoughts that can create new thoughts.
Small addition to make. You're exactly right that superstition, as we probably would say, the byproduct of the architecture that humans use. And I mean, the process of scientific inquiry is also requires to make abstract, invisible, but inferable intermediate states or processes. I mean, it can be used both way, but the procedure that somebody uses is the acceptance of some belief without.
Sorry, you are talking 10 minutes.
Sorry there.
We can discuss later.
I'm sorry for interrupting you, really. You see, you are asking to develop new techniques, but it is well known that new is well forgotten old. Yeah, it's just a joke, of course. I just should remind you that probably one of the first theoreticians who dealt with recurrent networks was David Marr. It was 11 years before Hopfeld, you probably know. And again, with David Marr, you know his general idea about hippocampus. The general idea is that as soon as you are just getting all the world, you have proper or improper level of understanding it. Yeah, somehow. But it is reflected by, say, the level of activity of higher centers. And those moments which are poor represented, they're just stored in hippocampus and replayed during sleep. This is one of the good ideas which probably is not yet explored here. Yeah, that's good.
Well, there's a lot of like ideas that are like motivated by the neuroscience, and it's also like very difficult. Like if we would completely like ignore the structure of the real world that the human brain is part of, that maybe we will be missing something on the prior knowledge that make our like efforts to get the like kind of like AI that is more like human-like easier. So definitely there are like this concept like why we sleep and how the long-term memory is actually formed. Actually, I don't think that people actually know the answer. Like I did read some articles about it.
Yeah, but that's one of the guesses.
Yeah, exactly. I think that the guesses are like going like as you were saying that during the day we accumulate some like memory in the hippocampus, and during the sleep it's just flushing it into long-term memory where it's getting stored
and obtaining filters which help with deal with badly represented situations. And
which is again probably large.
Yeah, so, and one more question, I'm sorry. Have you made some real step forwards after that paper which you published in November?
We had it at NIMS in December, so yeah. So of course we did publish it actually originally.
Yeah, but you have you any results in this roadmap? Any new ideas with this roadmap?
We have like unpublished things that we are thinking of. I wouldn't say that there's like some breakthrough. We were like discussing a lot, and it actually got later published by our group. The parallel memory architectures, like not the stacks, but more like store automatons that we would try to learn. It will be based pretty much on the same things, but you will be able to like get better time complexity. That's one of the interesting directions that we are thinking of basically.
Sure, definitely. It is very
but it's just a small thing. It's still, you know, like I would like to see a model where you store what you learned in the long-term memory, and still, as I was saying, like if you think of the stack RNN, that you have like the controller, which is the recurrent network, and then you have the long-term memory. And still the logic about the binary addition is learned in the controller. It's not learned in the long-term memory. And I would like to do it other way around. And it's not clear to me how to do it yet, but maybe later.
Yeah, and I just want to congratulate you that you are forcing on this road and insistence that the task should be challenging. Yeah, thank you.
And not too hard.
Okay. You should go here because you should use this microphone.
Yeah. So my question is connected to some previous about representation learning and supervised learning. So nowadays it's a lot of research is going in computational cognitive science about one-shot learning and all this stuff. And it seems like people suggest that it's better when in our latent representation there is some kind of real world structure learned, like a graphical model of like what caused what, and people showed that gradient descent or like this optimization method that we used to use, they don't work like we want, and they use other methods, optimization method like sampling and MCMC algorithms. So do you think that this like intelligent machines of the future will still use gradient descent or backpropagation algorithms, or they will move to some other methods?
Yeah, that's also an interesting question. I actually was always a bit skeptical about like what SGD itself, like how far can it take us. I mean, it's very interesting algorithm, but you can see that's basically some specific like version of search algorithm that is very like greedy hill climbing. Basically, it's hardly anything else than that. Even when we were learning actually these patterns like the binary addition, we did have to combine the SGD with more like search techniques in the sense that the model can get stuck in the local minimum. So if you, for example, add noise or you add more stacks, so that has larger search space, sometimes random restarts if it gets stuck somewhere. And we did actually use like these simple hacks too. And also in the appendix of the paper, we have like purely search-based techniques that are described there that also work for many of these problems, which is all like super old result. So we are not even claiming that we are the first ones, just that in these settings, it's possible to learn things. So SGD, in my view, is like a special version of search, and there's of course very efficient. That's actually the point of SGD. But besides that, it's quite greedy, and it has the local minima problems, which can be quite painful, especially for this type of problems that are very like algorithmic and where there are like these fake solutions that are not really optimal ones. So I think in the future it can be very well so that we will have to basically abandon the SGD and backpropagation, even if now like all the people working in networks would hate me to say it, but I don't know. So far I'm not completely convinced that it's the end of the story. Maybe there are very simple things just like search that will be used, just searching different space that would allow us to basically create a solution by the creating models that can really create some other components. This is kind of like what I would like to see, and still we don't have it. And that's also, in my opinion, like the solution to unsupervised learning. Basically, once you learn how to write basically and create thoughts, we can call it like that, then you can like get a system that can get just kickstarted in the beginning, and then it can like explode in complexity based just on the unsupervised signal is coming. That's like kind of like my dream. I don't know we will get there, but if it's true, then we don't really need SGD and backpropagation to backwards of some gradients. So we shall see. Who knows?
Questions?
Yeah, and in this respect.
Виталий Львович, давайте еще. So, nobody wants. Okay, one short last question.
In this respect, what do you think about the work of Lillicrap et al.? Lillicrap. They have alignment, stochastic alignment or something like that. They published that in November 2014 without Lillicrap. He is now with DeepMind.
I see.
Yeah.
Lillicrap,
Timothy Lillicrap. Okay, I'll write you. Thank you.
Before we thank our guest, I just want to remind you that Tomas gratefully agreed to have some informal talk after his lecture. I think that we will have break now for some coffee, tea, and then we'll just gather here who want to talk with Tomas and just have some talk. And now just say thank for the great lecture.